In this video, we're just going to walk through a few basic classes of functions, talking first about the most basic class of function that we're pretty used to already, which is linear functions. Now, linear functions have the form f of x is equal to mx plus b, where m and b are constants, and f is a variable. So we'll start with the definition. Let's consider the line L, which is passing through points x and y. Let's say x1 and y1 so that we can say x2 and y2 is the other point we're passing through. Then we say m is equal to the change in y. Here I have delta representing the change in y over the change in x. And we know the change in y over the change in x. We know that change is just subtraction. So what we end up with is the change in y is the second y minus the first y. That's the distance between those 2 points. Over the change in x minus, over the change of x. And so this represents the slope of the function. One more definition. Something useful to keep in mind is that given a point, x1, y1, another way to represent the line is to write y minus y1 is equal to m times x minus x1. And we call this point slope form. We call y equals mx plus b slope intercept form. Because we have m here being the slope, and then we have b here being the y-intercept, or the y value through which the line runs. And then lastly, we have ax plus by equals c is what we call standard form. So all of these represent the same thing. They all represent the form of a line, equations of a line, and they give you different information about that line. Now, another class of functions that we know are polynomials. And polynomials have a general form of the following. F of x is equal to sum an, which is a constant, x to the n, plus an minus 1, x to the n minus 1, all the way down until you get to a1, x to the first power, plus a0. And if n is 2, if our highest degree of the polynomial is degree 2, then we have a quadratic function. If it's degree 3, we call it a cubic function. And after that, we say nth order. So if I have an 8th order polynomial, I call it an 8th order polynomial. Now we know some things about polynomials. If I have, for any f of x is equal to ax to the n, if n is even, we have an even function. And if n is odd, we have an odd function. So we know the most basic version of a polynomial equation. The one that you see quite a lot is a parabola, which is a second degree polynomial. And a second degree polynomial looks something like this. Here we have the basic y equals x squared. And now one interesting observation is if I throw a negative sign up front, if I write y equals negative x squared, we just reflect along the x-axis. So we end up with a parabola facing down instead of up. Now a rule of thumb for polynomials is for quadratic functions is given ax squared plus bx plus c equals 0. We know that we can find roots of this function. This function will always have roots, but sometimes they won't be real. And when they're not real, they're a lot harder to factor. But we always have this nice formula, the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we call that the quadratic formula. Now let's say I wanted to graph a function. Let's say I wanted to graph, for example, f of x equals negative 2x squared plus 4x minus 1. If I want to graph this function, I can just plug it directly into the quadratic formula to find my x values for which y is 0, for which my function is 0. So my step 1 is setting this equal to 0. And when I do that, I can plug in negative b. I can plug into my quadratic formula. Negative b is going to be negative 4. Here I have a equals negative 2, b equals 4, c equals negative 1. So negative b is negative 4 plus or minus the square root of b squared is 4 times 4, which is 16, minus 4ac. 4 times negative 2 times negative 1, or just 4 times negative 2, or 4 times 2, which is 8, all over 2a. 2 times a is negative 2. And what we end up with here is negative 4 over negative 4 is 1, plus or minus the square root of 16 minus 8 is 8 over negative 4. So we have 1 plus or minus root 8 over negative 4. 2 times 2 is 4, 3 times 3 is 9, so the square root of 8 is somewhere between, square root of 8 is greater than 2 squared, which is 4, but it's less than 3 squared, which is 9, so it's somewhere between 4 and 9. Sorry, let me flip this. It is greater than 4. And so we end up with something to the left side of 0, something to the right side of 0, and we have a parabola. And another thing we know is that there's a negative sign out front of the x squared term, so we know that parabola is pointed down. So we get a parabola that looks something like this. Now, I could have higher order functions, and a cool rule about higher order functions is as you go up in degree, you go up in bumps. So here I have an x squared function, a function that has an x squared, and we see one minimum or maximum. We see one bump. If I wanted to graph something like x cubed minus 3x squared minus 4x, I would get something that looks like this. I would go up, down, up, and I would get a function with 2 bumps. Now I could find exactly where those 2 bumps are with this exact function because I know that this is equal to x times x squared minus 3x minus 4, And we can use the quadratic formula again on x squared minus 3x minus 4. So let's draw a better graph. Negative b is going to be 3 this time because b, here we have a equals 1, b equals negative 3, c equals negative 4. So I see negative b is going to be 3, plus or minus the square root of b squared is going to be 9, minus 4ac is going to be 4 times 4, which is 16 with a negative sign because we have negative 4 in our c, all over 2a, a is 1. So if I work this out, I get 3 plus or minus the square root of 25 all over 2, which gives me 3 plus or minus 5 over 2, which gives me 3 plus 5 is 8 over 2 is 4. 3 minus 5 is negative 2 over 2 is negative 1. And so what I just found is I have a value at negative 1. I have a value at 4. But if we look back at our function, where else is this function equal to 0? Specifically when x is equal to 0. So we have a third 0 this time, right here. And now this is an odd function. There's no negative sign out front, so we're going to be coming from the bottom left through negative 1. We're going to reach some peak, and then we're going to come back down to hit 0. But then we're going to have to come back up to hit 4 again. And so our function looks a little bit more like this. Now we have another class of functions that we will call algebraic functions. And an algebraic function is a function including powers, roots, and all of our math operations that we're used to. So, one algebraic function could be something like f of x equals 3x minus 1 over 3x plus 2. Or something like g of x is equal to 4 over x squared plus 1. These are rational functions. If I have a function with a power, we just saw a bunch of functions with powers, but if I have a fractional power like f of x equals x to the 1 over n, we call this a root function. Specifically, if n equals 2, we get our classical square root. So x to the 1/2 is equal to the square root of x. And something we have to be careful about with functions like this is we can find domains and ranges that are not always super easy to understand. For example, if I have a function like this, 3x minus 1 over 5x plus 2, and I want to know what the domain is, I want to know all the x values I could plug in. Well, I could plug in anything that's really high, like 100, a million, a trillion. I could plug in anything that's really low, like negative 100, negative a million. Anything that I could plug in that would give me a real numbers solution is in the domain of this function. But there's one troublesome piece, which is we could set the denominator equal to 0. We could end up with a 0 in our denominator, and the value that gives us that 0 in the denominator is exactly negative 2/5. If we plugged in 2/5, we would get a 0 in the denominator. Now let's say I want to find the range of my function. Y equals 3x minus 1 over 5x plus 2. I could start by just solving for x. I could work through and solve for x. So I could say this is y times 5x plus 2 equals 3x minus 1. 5xy plus 2y equals 3x minus 1. We can bring our x terms to one side. We get 2y plus 1 is equal to 5xy plus 3x. There's a negative sign here. I could pull my x out and divide, and what I'm left with is x is equal to 2y plus 1 over 3 minus 5y. And then we can do the same process. We can say, for what values of y do we not get a solution? And in this case specifically, y cannot equal 3/5. Y will not equal 3/5. And so that is the range of our function. Now, another class of functions that we worry about a lot less in our class specifically are going to be transcendental functions. And we're really going to talk specifically about three types of transcendental functions, which are trigonometric. These are the only three that we really worry about. Trigonometric, exponential, and logarithmic. And we will see a lot of ways to handle these things, but an example of a trigonometric function might be something like f of x equals sine of x. And an example of, say, an exponential function might be something like f of x equals 2 to the x. Now, one more, we have piecewise functions. And piecewise functions are functions defined by different formulas on different parts of their domain. We have different formulas on different parts of the function's domain. And an example of a piecewise function is f of x equals negative x when x is less than 0, and x when x is greater than or equal to 0. And you can take a minute and pause the video for fun and see if you can figure out what function this is here. It's a function that you know. This function is specifically when we're less than 0, for example, when we have -1, f of -1 is going to be, we're going to add another negative sign. So -1 times -1 is going to be +1. So at -1, we're going to have +1. At -2, we're going to be at +2. We're just going to be going up in a linear fashion to the top left. When we're above 0, we just have f of x equals x or y equals x. We have the simple line with slope 1. This is specifically the piecewise way of writing f of x equals the absolute value of x. This is the absolute value function. But it doesn't have to be that simple. We could have more complicated functions. So let's plot f of x equals x plus 3 when x is less than 1, and x minus 2 squared when x is greater than or equal to 1. So if I want to plot x plus 3 when x is less than 1, let's go to -1. If I plug in -1 here, I get a +2. I'm going to put an open circle because there's no equality here. If I plugged in -2, I would get -2 plus 3 is +1. If I plugged in -3, I would get 0, and we kind of see that we're going to get this line going off to the bottom left. Now when we're above 1, we have the function x minus 2 squared. Now something to remember about something like this is if I have the -2 inside of the square, what I'm going to do is shift to the right by 2, which means I have the regular parabolic function, which looks like this, and I'm just going to shift it right to the right by 2. So it's going to have its base here, and it's going to go up. Specifically, this function at -1 is going to be all the way up at 9. This function at -1, if I plug in -1, I get -1 minus 2 is -3, squared is +9. So this is going to go all the way up to here. Oh, I solved with -1 instead of 1, but let's just add the -1s to that function. And that is all of the types of functions we are going to look at in our class. We're going to look at transcendental functions, piecewise functions. So piecewise functions will be important. Things like trigonometric functions will be very important. We will see a lot of algebraic functions for which we have to understand their domains and ranges. Polynomials are going to be always the simplest examples. And then, of course, no math class is complete without lines, without linear equations.